If you're a committed flat earther or just flat earth curious and watch this video to the end, I'm going to take something away from you and offer something in return. It'll be up to you to decide whether the exchange is worth it, but what I give you will empower you to make better decisions and to discern the truth a bit more accurately. You'll see some videos of a ball soaked in some liquid spinning on a drill. Not surprisingly, the liquid will fly off the surface of the ball. The video will inevitably draw an analogy to the Earth spinning at over 1,000 miles per hour and ask you how the placid water in a mountain lake doesn't fly off into space. Clearly, the Earth must be stationary. There's a trick they're not telling you about when they make this comparison. I'm going to tell you what that trick is because you deserve not to be fooled. Now I know what you're thinking. Gravity? Seriously? If you don't accept gravity, that's fine. Think of it as dropity or gravity or buoyancy and density or whatever else. We can at least agree that things tend to fall toward the Earth, and that's all we need to agree on right now. But I'll call it gravity in this video. First, some background. On a rotating object, there are two forces at work that interest us. Centrifugal force is the impetus to be thrown from the surface of the rotating object. It's the force we feel pushing us away from the center of a merry-go-round. It's not really a force, but rather an inertial effect. This distinction isn't important for our purposes. Gravitational force is what causes things to fall toward the center of a large mass like the Earth. Both of these forces have formulas that describe them and which can be used to predict the behavior of an object being affected by these forces. These formulas have been tested, formally and informally, millions of times. We know they work, and the results you get from them can be trusted. Now, how can you tell by using these formulas whether some liquid on the surface of a rotating sphere will remain on the surface or fly off? Both formulas give you an answer in newtons. The comparison is simple. If the gravitational force is greater than the centrifugal force, the liquid will stay on the surface of the rotating object. If the opposite is true, the liquid will fly off the surface. In either case, the larger number determines what happens to the liquid. Velocity, or speed, is defined as the distance traveled over a period of time. The formulas use the metric system, so that's what we'll use here. For the purposes of this exercise, there are two types of velocity, linear and angular. Linear velocity is the miles or kilometers per hour we're all used to. Angular velocity is expressed as the number of degrees or radians turned per some unit of time, like hours. Now, suspend your disbelief for a moment and assume the Earth is a nearly perfect sphere. I'm going to throw some numbers at you, so stick with me. We'll round these figures to the nearest whole number for now because we just want to get a sense of the problem. More precision won't materially affect our outcomes at this point. At the equator, the circumference of the Earth is 40,075 kilometers, so the linear velocity of a person standing on the equator is 1,670 kilometers per hour. At the 45th parallel, north or south, the distance around the Earth is 28,337 kilometers, so a person standing at this latitude is moving at 1,181 kilometers per hour. You can see how it would be confusing to talk about the rotational velocity of a sphere in terms of distance per hour because the distance, and thus the velocity, changes depending on the observer's position on the sphere. So when we speak of rotational velocity, we use degrees per hour instead to avoid confusion. The Earth's spin at 15 degrees per hour, making it a complete rotation in 24 hours regardless of where you are on its surface. By comparison, the hour hand of a conventional clock moves twice as fast, 30 degrees per hour, going twice around the clock's face in 24 hours. How fast the tip of the hour hand is moving in terms of linear velocity depends on how long the hour hand is. An hour hand 15 centimeters long travels about 94 centimeters in 12 hours, or a bit less than 0.00008 kilometers per hour. An hour hand 6,378 kilometers long travels 3,340 kilometers per hour at the tip, but more slowly as you move closer to the center of the clock face. Both hour hands move 30 degrees per hour, regardless of how long they are. You can see the issue here. Using linear velocity to describe the rotational speed of an object can be misleading because it depends on the size of the object. A ball spinning on a drill isn't the same thing as the Earth spinning on its axis unless the ball on the drill is only turning at 15 degrees per hour just like the Earth. Already we're starting to see that the comparison between the Earth and a ball stuck on a drill isn't entirely honest. Let's dig a bit deeper. Let's start with water on the Earth. The force of gravity is described by this formula. G is the universal gravitational constant, and it's a very small number. M sub 1 is the mass of the Earth, and it's a very large number. M sub 2 is the liter of water that weighs approximately 1 kilogram. D is the distance from the center of the Earth to the center of a container holding a liter of water on the Earth's surface, and it's 6,378,000 meters. Crunch the numbers, and the force of gravity on the liter of water is 9.798 newtons. Centrifugal force has its own formula. M sub 2 is the mass of a liter of water. The velocity of rotation is a bit over 465 meters per second. And r is the radius of the spinning object, in this case the Earth. This is the same number as the distance between the centers of the two objects, because the fraction of a meter's distance to the center of the container won't make a material difference to the outcome. Crunch the numbers, and the centrifugal force on a liter of water is 0.03393 newtons. Compare the two numbers and it's obvious that the gravitational force on the liter of water is greater than the centrifugal force. The water doesn't fly off the surface of the Earth. Now, let's do the same set of calculations for a spherical sponge soaked with water. Assume a very absorbent sponge with a diameter of 150 millimeters, or almost 6 inches, soaked with 0.125 liters of water, about an eighth, which is about 4 ounces. The ball is mounted on a drill that spins at 300 revolutions per minute. The gravitational constant remains the same. The mass of the wet sponge is 0.4571 kilograms. The water's mass is 0.125 kilograms. The distance between the centers of the two objects is 0.075 meters. Crunch the numbers, and the force of gravity on the water on the surface of the sponge is tiny. It's 6.810 billionths of a newton. The centrifugal force involves the mass of the water, 0.125 kilograms, the rotational velocity of a 150 millimeter sphere rotating at 300 revolutions per minute, or 2.3562 meters per second, and the radius of the spinning object, 0.075 meters. Crunch the numbers, and the centrifugal force is 33.8353 newtons. Compare the two numbers, and it's obvious that the centrifugal force on the water is greater than the gravitational force, so the water flies off the surface of the sponge. Now let's take this analysis one step further. For an object to leave the Earth's gravitational pull, it has to achieve escape velocity. In other words, for an object to behave like the water on the spinning ball that flies off and spatters the wall, it has to move at a sufficiently high velocity to counteract the pull of the Earth's gravity. In addition, the objects we're discussing don't have their own propulsion systems like rockets do, so they have to get all their velocity from the Earth's spin. Here are the relevant numbers from observation 1. Crunch the numbers, and we see that the escape velocity from the Earth is a very high number, a bit over 11,000 meters per second. Compare this to the velocity of the Earth's spin, and it's obvious that the liter of water doesn't come close to achieving escape velocity. The conclusion is clear. Earth doesn't spin fast enough to throw anything off its surface into space. Of course, this matches our real-world observations. Never mind that a liter of water moving at 11,000 meters per second in our atmosphere would vaporize due to atmospheric heating. Clearly, the spinning Earth and spinning ball are not at all analogous to each other. The ball is spinning much too fast for the analogy to hold true. All the videos telling you otherwise are based on a false premise. Did the producers of these videos know this beforehand? If they didn't do these calculations prior to making the videos, they were sloppy, and you should ask yourself whether you should trust them without checking their work first. If they did do the research and made the videos anyway, they were dishonest, and again, you need to question whether they deserve your trust. A third possibility is that they were so excited by the idea that they rushed to publish their videos before thinking things through. You can admire their enthusiasm, But what about their judgment? I have my own opinion, but you should decide for yourself. Now we can go back to the exchange I alluded to at the beginning. What I've taken away from you, dear flat earther, is plausible deniability. Now you have no excuse to be fooled by the spinning ball trick. Every time you see someone try to sell you on the spinning ball trick, you have a duty to call them on it because they're peddling a lie. From the video creators who use the spinning ball trick, I've taken a bit of your credibility. A few more of your viewers will know that the rapidly spinning ball is actually nothing like the Earth. In short, they'll know that in this, at least, you're lying. What I've given you in return is knowledge, and knowledge is power. You now have the power and the responsibility to think for yourself a bit more clearly. You can calculate the numbers for yourself and decide, for yourself, whether what you see makes sense. Don't believe me? That's healthy. Find other scenarios like this and test the formulas for yourself. What happens if you're on a merry-go-round or one of those spinning playground rides? Figure it out. Do some research. Don't take my word for it. Don't take anyone's word for it.